Pressure reduction is necessary whenever fluids are transported at pressures that are greater than the pressures at which they are used. Natural gas, for instance, is transported in these pipelines at a high pressure, which is reduced at this station for branch distribution. It is again reduced at each customer's location to meet the differing requirements of hospitals, homes, commercial, or industrial establishments. Industry quite often uses this gas to produce steam, which also requires pressure reduction to be useful. The steam generated in this boiler is normally distributed at a relatively high pressure. The pressure is then reduced moderately when the steam is used to provide power, further when it is used to heat a product or for comfort control. When steam is used in a heat exchanger, the pressure is reduced because more heat is available for transfer from lower pressure steam. The total amount of heat contained in steam varies little regardless of pressure. However, this heat must be characterized in two ways. The saturated heat of water is the amount of heat required to make it boil. As pressure increases, more heat is required to boil the water, generating steam. The latent heat of the steam is the amount of heat in the steam given off before it condenses back into water. If the total heat in the steam remains constant with increasing pressure, while the saturated heat rises, then there is less latent heat for the steam to release at higher pressures. Since it is this latent heat that heat exchangers use, the steam saturation curve indicates that they should be operated at the lowest possible pressure to be efficient. Originally, orifice plates were used to reduce pressure. For any pressure and flow rate within a given diameter line, a hole or orifice of a specific size could be selected, which would yield a calculated pressure reduction. The problem was, however, both the upstream pressure and the downstream load were subject to change. If a manual valve were substituted, an operator, observing both the upstream and downstream pressure, could open the valve when downstream pressure dropped, close it when downstream pressure raised, open it when the load increased, close the valve when it decreased, open it, close. Well, you get the idea. All of this, of course, was costly, not to mention inefficient. The obvious answer is automatic control. One approach is the multiple component automatic loop. Let's go back to our valve. First, we sense the pressure downstream of the valve and create a signal that is proportional to it. Next, we add a controller which can compare this pressure signal to another that can be adjusted to indicate the desired pressure, called the set point. Now the controller generates a third signal that is proportional to the difference between the first two. This control signal operates a motor attached to our valve, and there you have it, a multiple component automatic loop. Of course, all of this equipment needs some sort of power, and it all must be piped and wired together. A second approach, which is simpler and much less costly, is the pressure reduction valve, or PRV. PRVs are mechanical controllers which provide all the basic functions of the loop in a single body and are powered by the medium they control. Many devices are used to automatically regulate fluid pressures at a preset level. Whether the device is complex or simple, there must be a common means to compare them, to select which one is best suited for a particular application. The pressure regulation curve does this. It plots the steam pressure as a function of flow rate. The lowest flow rate is achieved when steam is shut off downstream of the PRV, a condition known as dead-end shutoff. When this happens, the PRV reacts by closing, but not quickly enough to prevent a pressure buildup downstream. This is called lockup, and is characterized by the highest pressure reading on the regulation curve. Flow increases until it reaches the minimum controlled flow rate. This is the lowest flow rate at which a steady pressure can be controlled. The rated capacity is the greatest flow rate at which the PRV can maintain a controlled pressure within its specifications. The regulation curve centers around the set point, the desired regulated pressure. The amount the controlled pressure varies from the set point between minimum controlled flow and the rated capacity is called the offset, or the accuracy of regulation. There are several ways of defining the offset. It can be stated as a total percentage of accuracy, say 85%. A percentage of variance from the set point, 15%. Or it may be expressed as a percentage of deviation around a set point which is at 50% of rated capacity, plus or minus 7.5%. When comparing pressure reduction alternatives, it is imperative that the rated capacities are quoted at the same accuracy of regulation no matter how it is stated. Finally, we define sensitivity as the amount of pressure change that occurs before the valve reacts to control it. What are the advantages of the multiple component automatic loop with its greater cost, greater number of parts, and therefore greater opportunity for failure? The loop can operate within tighter tolerances. Pressure can also be controlled over a wider range, from a lower minimum controlled flow to a higher rated capacity. There are several applications where these sorts of tight specifications are essential. Turbines, for example, need precise pressure control, accuracy of regulation in the order of 0.1%. Process heat exchangers often need pressure precisely reduced over a wide range of inputs. Most applications, however, have neither the performance nor power requirements to justify such systems. In the majority of instances, one of the several types of PRVs available will perform outstandingly. There are two separate design styles for PRVs, each with a number of possible valve and actuator variations. Direct-acting PRVs are the least complex type. Like the multiple component automatic loop, there is a variable restriction orifice, the valve and seat. The downstream pressure is sensed through porting inside the body by one of several devices, in this case, a bellows. The bellows also serves as the controller because the outlet pressure is opposed across the bellows by the set point device, a regulating screw and spring. The bellows serves a third purpose, that of an operator. The valve is connected by a stem directly to the pressure side of the bellows and moves as the bellows flexes. Here's how they work. Clockwise rotation of the set point screw compresses the set point spring. Pressure from the set point spring on the bellows forces the valve open against the inlet pressure and a valve spring, which maintains contact between the valve and the body. When the steam passes into the outlet chamber, it contacts and compresses the bellows, restricting the orifice. The orifice size is regulated by the balance between the set point pressure above the bellows and the sampled pressure and the valve spring below. Increasing the set point pressure opens the valve further, increasing downstream pressure. If fluid usage decreases, the downstream pressure rises, compressing the bellows and throttling the valve. This reduces the outlet pressure until it again equals the set point force. In this way, the pressure is maintained at the set point while flow is reduced. When fluid usage again increases, the downstream pressure falls. The unbalanced set point force extends the bellows, pushing the valve further off the seat. The resultant increase in downstream pressure compresses the bellows until the forces across it are again balanced. Several variations to the valve are possible which allow it to be reconfigured for particular applications. The largest effect on the regulation curve may be seen by altering the controller. First, the longer the valve stroke allowable by the controller, the greater the stability of the PRV. Second, The larger the area of the controller, the larger the valve that can be opened, therefore the larger the capacity of the PRV. Third, the larger control area also responds better to small pressure changes. Fourth, the flexibility of the controller determines how quickly and to what degree valve movement is accomplished, affecting both accuracy and sensitivity. And finally, a limiting factor is placed on the PRV by the fragility of the controller. It bears the total differential pressure between the outlet chamber and atmospheric, so more flexible but weaker controllers may be damaged by high pressures. The simplest controller is a flat diaphragm. While inexpensive, this type of controller is limited in flexibility and travel. Diaphragm controllers are used in low pressure and flow situations where neither sensitivity nor accuracy is of much consequence. The slack or grooved diaphragm has a groove molded into the outer circumference between the diaphragm plate and the valve body. This slack area allows medium-length valve travel with increased flexibility, resulting in higher flows, sensitivity, stability, and accuracy than a flat diaphragm. A further adaptation is the cupped diaphragm, or Bellophragm. In this case, the diaphragm fits quite loosely over a cup, allowing a long valve movement and an increase in stability. All diaphragms, however, are made from relatively thin stock, which severely limits pressure. Next, we have the already familiar bellows. As a controller, bellows offer longer valve travel and greater flexibility than the flat diaphragm. Bellows are also limited in pressure handling, but are stronger than the diaphragm. The bellows can be mounted in the body so that the pressure is either internal or external. A bellows with the pressure on the inside is more likely to burst in high pressure. A bellows with high pressure on the outside may have the convolutions crushed, making it inoperative, but it will not burst and pressure integrity will be maintained. The most expensive controller is a metal piston which moves in a cylinder. The space between the piston and the cylinder wall is sealed with a ring, much the same as in an automobile engine. This method allows both a long stroke and high flexibility while being able to serve in severe pressure situations. So much for the controllers. Now let's look at the valve plug and seat. These components not only affect the regulation curve, but must be selected for the type of fluid to be controlled and the desired tightness of the seal at shutoff. A single-seated, unbalanced pressure valve is the simplest and least expensive design. The term unbalanced pressure indicates that when the valve is closed, upstream pressure to the PRV is entirely brought to bear on one side of the valve. On the other side is the force of the set point apparatus and any back pressure in the system. In other words, the pressure across the valve plug is unbalanced. It is this pressure imbalance and its effect on fluid as it flows through the valve while it is opening or closing that most limits the use of this design. When the controlled variable is a liquid, the valve must be arranged so that it opens in the direction of flow. Why? If the valve opens against the flow, all of the upstream pressure serves to hold the valve closed. In order to overcome this pressure, greater force must be exerted by the set point spring to open the valve, and the spring force pushes the valve wide open. Immediately, there is full flow rate. While the PRV will eventually react to reduce the pressure, its initial response has let loose a high-velocity slug of non-compressible liquid. This is a classic example of water hammer. If the valve opens in the direction of flow, the pressure works to open the valve, and these problems do not occur. However, only the force of the valve spring is available to close and seal the valve, so soft seats or soft valve plug inserts, which erode easily, must be used to ensure tight shutoff. A similar problem may occur with liquids at very low flow rates, even when the valve is properly configured. As the valve begins to close, its throat area becomes restricted. The pressure in the throat area drops as a result of the Venturi effect, slamming the valve into the seat. The immediate cessation of pressure in the sensing chamber causes the valve to snap open again. The valve continues closing and opening rapidly in a chattering fashion, and again, water hammer and damage to the valve may occur. When the controlled variable is a gas, which is subject to expansion and compression, the valve should open against the flow, using the upstream pressure to help seal the valve. Gas expands in the low pressure area immediately downstream of the valve when it begins to open. This pressure increase serves to quickly throttle the valve, preventing it from opening fully. When there is low flow, the downstream pressure increase prevents the valve from fully closing. In either case, since gases are compressible, unlike liquids, there is a cushioning effect, so water hammer is not a problem. If the fluid is steam, its erosive nature dictates metal seats and valve plugs. Greater force is needed to seal the metal-to-metal contact. This is best provided by using an unbalanced pressure valve with the valve opening against the flow. No matter what fluid is being controlled, the flow dynamics of a single-seated unbalanced pressure valve make it sluggish, inaccurate, and sensitive to inlet pressure variations. Additionally, the pressure imbalance makes them unsuitable for high pressure or high capacity service. For liquid service, where tight shutoff is required, the best choice is a single-seated pressure-balanced valve. There are two possible designs for these valves, but both of them are suited only to open with the flow. The advantage of this configuration is that the inlet pressure is distributed to both sides of the valve, so there is no pressure differential. This ensures easy valve movement at any pressure. The result is better regulation accuracy, increased sensitivity, and greater stability at low flow. The first design we'll look at features a plug that extends to form a piston the same diameter as the seat. The piston is sealed within a closed cylinder by an O-ring. A hole drilled through the center of the length of the piston allows the upstream pressure to be distributed equally on both sides of the valve. The space behind the piston also provides for a dashpot effect, which has a tendency to smooth out valve movement. The second design also uses a piston the same size as the seat, but this time it is attached to the upstream side of the valve by a stem. The upstream pressure pushes on both the valve face and the piston equally, balancing the pressure across the valve. Some PRV applications call for control of a high flow rate of either gas or liquid in a limited space. If the situation doesn't also require tight dead-end shutoff, a double-seated pressure-balanced plug is the preferred valve arrangement. The inlet pressure is distributed between the seats of two interconnected valves, one opening with and the other against flow. Actually, practicality demands that the top seat be slightly smaller than the bottom seat for ease of assembly and disassembly. This prevents the valve arrangement from being perfectly balanced, but doesn't have much effect on the regulation curve. Tight shutoff is virtually impossible for a dual-seat valve because of manufacturing constraints. The only possibility we've discussed so far that is suitable for steam service applications is the single-seated, unbalanced pressure valve with all its inherent inaccuracies. However, as I mentioned before, there is a second design style for PRVs. This is a pilot-controlled pressure-reducing valve. The notable difference is all the internal channeling and this second independent valve. There is one other notable difference, the regulation curve. As you can see, the pilot-operated valve has greater flow capacity and better accuracy of regulation. They are also capable of performing under much higher inlet pressure than direct acting valves with offsets similar to automatic control loops. In order to understand the workings of a pilot-operated PRV, let's once again compare it to the components of the loop. A diaphragm-type direct-acting valve, called the pilot valve, acts as the pressure sensor and controller. Downstream pressure is channeled to the underside of the pilot valve diaphragm, where it provides a force in opposition to the set point spring compression. A difference between the two forces moves the pilot valve. Inlet pressure is also channeled to the pilot valve. The movement of the pilot valve varies this pressure. It becomes the control signal, which is directed from the pilot valve to the top of a large piston, which serves as the operator of the main valve. The pilot-operated PRV has two distinct advantages over the direct-acting type. First, the short travel of the pilot valve allows the use of a metal diaphragm suitable for high-pressure service. Secondly, the relative difference in size between the main valve and the piston operator serve to amplify the control signal. This amplification allows the main valve to open easily against high pressure because even though the inlet pressure opposes opening of the main valve, the amplified control signal of the controlling piston provides enough force differential to easily open the valve. Here's how pilot-operated PRVs work. By increasing the force of the set point apparatus, inlet pressure on the small pilot valve is overcome. A small movement in the metal diaphragm pushes open the short travel pilot valve from its seat, and inlet pressure flows to the top of the piston, opening the main valve. At this moment, the outlet pressure reaches the bottom of both the pilot valve diaphragm and the main valve piston. Outlet pressure on the diaphragm counters the set point force, throttling the pilot valve and dropping the operator control pressure. Concurrently, outlet pressure at the bottom of the piston and the bleeding off of pressure above the piston serve to close the main valve. When outlet pressure on the diaphragm equals the set point force, the pilot valve stops moving. Flow through the pilot valve balances with the flow through the piston, and the piston stabilizes with the outlet pressure on both sides of it. When the downstream load decreases, outlet pressure rises. This pressure increase is sensed below the main valve piston and pilot valve diaphragm simultaneously. The diaphragm throttles the pilot valve, decreasing pressure above the piston at the same time pressure below it increases, closing the main valve until the outlet pressure is once again in balance with the set point force. If load increases, pressure decreases below the piston and the diaphragm simultaneously, and the reverse occurs. The set point force on the diaphragm opens the pilot valve, increasing the pressure above the main valve piston. The resultant differential pressure opens the main valve until the outlet pressure matches the set point, and the pressures on both sides of the piston are in balance. If the contact between the piston operator and its cylinder wall was the only seal between the inlet and outlet pressures, the large surface contact area could cause excessive friction against movement of the piston. Even very small dirt particles could keep this valve from moving. The solution is a loose-fitting piston supplied with a sealing ring, just as in an automobile engine. This piston ring also scrubs the cylinder wall as it moves, preventing dirt buildup. A special advantage of the pilot-operated PRV is that the long stroke of the main valve allows the use of a cage valve in which the shutoff surface is independent of the fluid control surface, which is 4 circular ports in the side of the cage. The valve must move off the seat or sealing surface before the flow controlling port is opened. The sealing plug is off the seat before flow begins. Therefore, the wear caused by high velocity flow through a partially opened valve at startup or at low flow operation occurs only at the flow control port and not at the shutoff sealing surfaces. The multiple circular ports also reduce noise and characterize the valve. If the port were square or rectangular, each increment of movement of the valve plug would cause an equal change in flow. With circular ports, the port area opened at the beginning of the stroke is much less than later in the stroke. Flow changes less in the beginning of the stroke, so the valve is less sensitive to turbulence in the pressure signal and maintains its stability during low flow operation. An alternative to the piston operator is a diaphragm. A diaphragm can be of much larger area than practical size limitations permit in a piston. Therefore, a diaphragm operator can open a larger valve. The result is greater capacities for a given body size. The PRV works in the same manner as before, but the large diaphragm does present some potential difficulties. Usually, the control signal to the main valve diaphragm and the bleed passage are external. This makes these valves more cumbersome, but easier to clean. Another difference is that since the diaphragm must be metal in order to tolerate high pressures, a short stroke main valve must be used. This always results in less stability, poorer regulation, and an increased sensitivity to small pressure changes. With the large diaphragm to sense outlet pressure variations, turbulence at the outlet of the valve can cause instability, valve chatter, and excessive wear at low flows when the valve must work close to the seat. This limits flow rangeability. The internal pilot piston-operated PRV has several advantages that make it a good choice for steam system service. It is comparatively small and inexpensive to purchase and install. It exhibits excellent accuracy and sensitivity, is highly stable at all flow rates, and has a long service life. The main disadvantages of internal pilot-operated valves is that the internal piping is small and may plug up with dirt. Cleaning these devices always requires disassembly. Therefore, care should be taken to provide as clean an operating environment as possible, notably by installing and maintaining an upstream strainer. This leads us to our final variation, the externally piloted valve. Either piston or diaphragm-controlled main valves may be used for this variety, which features downstream pressure sensing removed from the body of the PRV and therefore from any valve turbulence which may occur. Under ideal conditions of piping with long straight runs and stable sensing points, this may provide better control. However, long, small diameter sensing lines may result in a delay in sensing pressure changes and in slow reaction by the valve. The inlet pressure sensing line may be located in the body or piped external to it. The pressure bleed line across the diaphragm is piped externally. The external piping makes this type more expensive to install, and a small stabilizing orifice mounted in this line can plug. The pilot valve may be mounted on the main valve as an integral part of it, or it may be mounted separately beside or away from the main valve when space limitations dictate. The external mounting also results in more piping and higher installation costs. External piloting permits the use of various types of pilot valves for pressure, temperature, back pressure, differential, or other control using the same main valve. Nonetheless, the installed cost is much more expensive than an internal pilot valve. PRVs, while simple, efficient, cost-effective, can fulfill the majority of your pressure reduction requirements. They may be configured to provide the needed control for liquid, gas, or steam media with excellent accuracy and long-term dependability. At Armstrong, we can offer you a wide variety of PRVs for most applications and the knowledge to apply them correctly. Contact your Armstrong representative for more information. At Armstrong, we believe that knowledge not shared is energy wasted.